All right, so as Tillman very nicely said, I'm the token experimentalist here. No, I'm not the only one. I think there are a few of us. But as the first experimentalist speaker, my job is to kind of tell you how we make sense of our data. I mean, the data you guys never get to see, or you will eventually when we do the whole open data thingy. Can you hear? Is it fine? Okay. Yeah. So this is a quote from, I mean, this is not a quote, but this is something Jesse Thaler used or still says. In 2015 or even earlier, so there is this meeting in Les Jours. I don't know if anyone of you been to that. It's like on French Alps. You stay isolated for 10 days and do physics. This is not a workshop in the true sense of the word. There are no scheduled talks. People just decide on projects and work on those. And I have spent at least 2 lectures working with Jesse, learning things. And at the end of the day, I think our whole thing was, all of us, his minions, our aim was to please Jesse. And at that point, Jesse used to say, "Hello, deep thinking always beats deep learning. I don't know why we are doing machine learning. It's a new fad. It's not physics." And then I think, so that was like 2013 or 20, yeah. I think in 2017 when I was last time in Les Jours, or no, 2019, whenever. I think Jesse has come around, he has become a convert, and he is like, no, I think in the middle he was like deep thinking is complemented by deep learning. And then finally he went to the phase like, no, deep learning is the way to go. He's the director of the institute in Boston, right? So before all of that, I just wanted to kind of do an introduction to who am I, because every person I met was like, what do you do? And I'll come to that. So I grew up in India, Calcutta more specifically. That's a picture of my campus. Then I did my PhD in Florida, Gainesville to be precise. That's a picture of a space shuttle launch at 3 a.m. at night. Now, as physicists, you all know light travels faster than sound, but that was like a real exhibition. We are 10 kilometers away from the launch point. The whole world lit up, and then we heard the noise a bit later. Then, like every particle physicist, experimental particle physicist, I spent a bit of time at CERN. I did postdocs in Dresden, Germany, in Glasgow, and from 2015 onwards, I'm in Johannesburg, South Africa. As I say, typically have not been killed, mugged, shot. So, I mean, South Africa, if you Google, that's the impression you get, which is not entirely untrue, but nothing bad happened to me. And a lot of people were asking me yesterday, like, what do you do? So I thought I will explain, I mean, this has nothing to do with machine learning, but this is a nice physics thing we did in last 2 years. I heard quite a few people in the introduction mention dark matter. So now, historically in colliders, the way we looked for dark matter is what we call mono-X signatures. You have large missing energy. How many of you know what missing energy is? Okay, awesome. Most people know, that's great. And you have a dark matter particle which is giving you the missing energy. It's balancing against some standard model object. Take your pick, quarks, gluons, top quark, Higgs, photons. Like we have done enough mono-X searches. That's like a classical signature in our detector, like you would expect the dark matter particle to be here, some jets, standard model objects to be there, and we haven't found it. So rather than that, we tried to look at a scenario which is called strongly interacting massive particle scenario, where rather than having just one WIMP or set of WIMPs, you have a replica of QCD. So the standard QCD with quarks and gluons and hadrons and strong interaction, you have a replica of that in the dark sector. So you have dark quarks, dark gluons, essentially a dark QCD. They interact strongly among each other, as you would expect in QCD. And so this gives rise to a whole new world of phenomenology. Now, of course, this is wild west, because in normal QCD, you have experimental constraints, right? You know how strong the coupling would be and everything. Here, no one knows anything. We set them to normal QCD-like values, but who knows? Anyway, so essentially the signature we have, we looked at T-channel, CMS had a S-channel result before. S-channel result is almost like a glorified digit resonance search, but the one we looked at is you have a scalar bifundamental mediator which gives rise to two dark quarks, and these dark quarks decay partially back to standard model hadrons, partially to dark hadrons. So the HV stands for Pythia hidden valley module, which you don't need to worry about. It's like the Pythia module you use to do dark sector showering. So at the end you have two jets, at least in the leading order, and those are composed of dark hadrons and standard model hadrons. Of course, I'll go more details into that. The jet formation is only using standard model. Dark hadrons we can't see, but they are there. So what happens is you get a signature like this where you have two, we call them semi-visible jets because there's a fraction of dark particles inside the jet, and the missing energy, which is a red arrow pointing along one of the jets. Now, as a theorist, which most of you are, you don't see why this is a problem. Well, if you're an experimentalist in Atlas or CMS, this is a huge problem. These are the events we never look at, because whenever we see missing energy aligned with one of the jets, we throw those events away because those are signatures of mismeasured jets. Jets hitting like a part of the calorimeter which is inactive or doing something bad, and we are like, oh, throw these events away. But that's our signal. This is of course, probably not a semi-visible jets event, but that's how the events would look like. And of course, because it's LHC, because there's radiation and everything, you'd have extra jets. So that's the kind of signature we were looking at, or we looked at. I'm going to spare you of the gory experimental details, but as I said, this is not typically something we looked at. I think I'm going to spare you all the details, but essentially say that we set the first limits. I'm going to explain what limits are in 10-15 minutes, and that's my PhD student. She was super happy not finding semi-visible jets, simply because if she did, she would not have finished her PhD in time. That's how experimental collaborations work, sad but true. If you find something where your expected background, your data doesn't match with your background, then you're in a world of pain. So it's cynical but true. Anyway, so that's what I did, or we did, for last 2.5 years. The first result in T-channel, I'm not going to do that, but yeah. So what's the plan today? Kind of like setting the scene. But before that, let me ask you a question. When was machine learning first used in experimental particle physics? Maybe it's obvious. How many of you think it's A? Okay, I'll give it time to read. No one. Oh, there is one.
No, decision trees count as machine learning, right?
Yes.
Okay.
Yes. So not A, right? How many of you think it's B? I have 1, 1.5, 2.5, 3. How many of you think it's like really, really early? Before all of you, not Tillman, but everyone else were born. That is the answer. It surprises people, because a lot of times you guys, cool kids, think this is something which started in last 5 years. No.
So you're including MBA techniques as machine learning?
I'm going to show you papers, screenshot of papers. I have receipts. I mean, this is essentially the whole idea, right, which I think David was kind of alluding to. Like, of course, the computing power has increased many-fold, which is allowing you to do this super n-dimensional curve fitting, which, to borrow his term. But that doesn't mean that we have not been doing this. So, I mean, this may not be the earliest, but this is one of the earlier ones I found. LEP, E plus E minus collisions, 1997. So that was one of the first experimental papers I found. And even like those guys had packages like you guys use. And they were using B-tagging. They were using this JetNet network to do B-tagging back in 1997. But digging deeper, no pun intended, you have CERN School of Computing in 1993, where there were like presentations on neural networks. I mean, people were talking about these things. Leif had a paper on JetNet, which is again quite early. And then this is a screenshot from CERN. I couldn't find a link to that, but apparently there's AIHENP, which I think is high energy and nuclear physics seminar in 1990 at CERN. I couldn't find a link to that. So yeah, I mean, this is going on when I was in high school, not even high school, in middle school. So this is quite old. I mean, TMVA, yes, BDT, yes. I mean, people have been using those in LEP and in Tevatron. And of course, Higgs discovery, there were contributions to that, but yeah. Right, so you guys are theorists. Most of you are, right? You want to, I mean, build models, calculate things, use machine learning to tell us what to do. I mean, at the end, I'm being very selfish, but I think your whole goal is to please us. Give us, because sure, you can have your fancy anomaly detection algorithm. If that doesn't work in data, is it useful? For you, yes, you graduate, you get a paper. But is it useful for the community? I don't know, I'm biased. So whatever tools you develop, whatever models you develop, if we can't search for that, if we can't make use of that technique, what's the point? Experimentalists, on the other hand, we have to dig deep to find anything. I mean, as David was mentioning, it's hard. I mean, it's hard for many different reasons. One of the reasons being you don't get what comes out of the collision, and I'm going to give you an example. Before that, so searches. I mean, of course, we all do searches, and I would probably categorize it from an experimental point of view of something which is very model driven, like SUSY, UH, lots of those. I'm not going to go into, oops, why my connection is lost. Yeah. And then there are a lot of, I would say, signature driven searches. For example, the same visible jet search we came up with, sure, there is a theoretical framework, but I was trying to look at events which people typically do not look at. People do not, and then you try to see what kind of models are there in the market which you can use to do the search. Because in LHC, if you want to do a search and if you go to the physics coordinator of the experiment and say, I want to look at events where there is missing energy close to jet, they would be like, are you crazy? Go away. If you say, I want to look for same visible jets, they're like, oh, that sounds cool, let's do it. So you always have to have a model. So of course, there are many models which are, the division is kind of artificial, but a lot of times we just look at resonances, which I think David was mentioning. You just expect a bump in a mass, typically a mass spectra, but there are a lot of other signatures. I mean, many of you must have heard or worked in this long-lived particle searches scenario where you expect your particles not to decay right to the center of the detector, which we call prompt, but have a longer lifetime, and that can extend from our, rather than decaying at the center, it can decay in the tracker, it can decay in the electromagnetic calorimeter, hadronic calorimeter, muon chamber, under Geneva Lake, wherever it is. I mean, you can build any models and then they would have specific signatures. So that's something people are doing more and more. But let's start with a simple example. So let's say we are searching for vector-like quarks. You are a theorist, you are very familiar with Feynman diagrams, so I don't think I need to explain that. So you have essentially capital T or B, which is your fourth generation or like vector-like quark, let's do that. And then they can decay to a top and a Z, or a top and a V or H. So there are lots of possibilities, and that's one of the things we have to deal with as experimentalists. Any signature can have different decay channels. So that's what you guys think, right, when you are thinking with your theorist hat on. The question is, what we are going to see in the detector? And whatever machine learning algorithm you are developing, if that doesn't work in whatever we are seeing in the detector, then that's not useful. So first of all, we don't get what is coming out of the collisions, because things decay, things interact with detectors. As I said, finite lifetime of particles, some particles decay promptly before reaching the detector. And also detectors are detectors. They have finite resolutions, dead cells, the magnetic field may not work sometimes, which happened with Atlas Now and CMS in run 2, sorry. So if I try to see how those particles, which we just said decay, and again, there are different decay modes, but I just picked an example. So Z can decay to L plus L minus, as you all know. The top can decay either hadronically or leptonically. Just to cover the whole set of examples, I said one top is decaying to hadronically, so QQB. The other one is doing L plus nu minus B, and the H, the largest decay fraction is BB, as you definitely know. So these are the things, and now as a theorist, maybe you are still okay with this. This is what you see, but this is not what we see. We see jets, as Tillman was saying. The quarks would give jets, B quarks would give B jets, which is slightly different from other jets. We'll come to that. The neutrino would give something like missing energy, which you said most of you know. The lepton would probably be detected as a lepton, E plus or E minus. If it's a tau, it's a whole new ballgame altogether, because tau is unstable, as you know. It can either decay hadronically or leptonically. If it decays leptonically, it would just look like other leptons. We typically don't even bother tagging the leptonically decaying taus. We do for hadronically decaying taus. So each little blob is a jet, and we'll explain what those are. Also, there may be another scenario where that top quark is boosted, which means it has a very large momentum. Then what happens is, I didn't draw it properly, but those three decay products would be like more collimated, squished together, and they would all be part of a jet, but which has a slightly larger radius. Again, I'll come to that. So as an experimentalist, we have to figure out which decay mode we are looking at, large radius jets, small jets, how many B jets. I mean, there would be a small B jet inside that, all of that. So yeah, so and this, if the Higgs is boosted, these two would also be part of a, can be part of a large radius jet. And then we also have the combinatorics problem, which essentially means, this is more for actually this one, if I go to that. When you are reconstructing your top quark, you need to pick the right QQB, right? If you don't pick the right QQB combination, you are not getting the top quark. The thing you reconstruct would not have the top quark mass. It would have a random mass, and you would immediately classify that event as a background, not a signal. So that's the other issue. I'm going to spare you all the details, but just to show, I'm not going to go over it, but just to show, like, when you do an analysis, we have to do a detailed selection on all the objects, their PT, eta, and we divide it into different, I'm going to come to that, signal control regions and all of that. From that, you essentially make a plot. That's what we do, that's our currency. In this case, this is like HT, which is sum of some PT of all the jets. You plot the data, and some way you estimate the background. We'll go to that at some point. And then you do that. And in this case, I think there is some discussion about if you have some signal at the edge. I mean, here you can get very excited, or you can just say we don't trust, where we don't trust the data points at the estimation at the very edge of the distribution because statistical uncertainty is enough. So I won't get very excited about new physics here. Some people do.
Which bin should I be excited about?
I mean, you can say, I mean, this is a large error bar, but I mean, it's just not touching. I mean, you can, right? You can say, oh, there is maybe new physics at, I don't know, HT of 1900. But I mean, for me, it's like not really. I mean, there's a large error bar, and it's towards the bins. Also, I mean, this is a log scale plot, right? So even though it looks like there's only a few less events here, it's 1.5 to 2 orders of magnitude, less, right? So yeah, as experimentalists, we have to be very, very careful about not over-interpreting things. And from that, you get this nice, I know there is someone from Brazil. This nice, what we call Brazil plots for obvious reasons. Now, and this is our results. Now, before I go into that, how many of you know how to read a plot like this? Not too many, right? So I'll probably go over it. It might be helpful because, again, you want to understand the results I'm presenting to you, I as in the experimental community. So I'll explain that. Yeah. So let's take this limit plot. There's a lot going on here. Like there is a lot going on here. So first is, let's look at the x-axis. Mt, which is a transverse mass, but forget about that, it's some kind of mass. So what we are looking here is some kind of mass of the new particle, right? So that's in my x-axis. The y-axis is the cross-section, and experimentalists will use cross-section as a proxy for number of times that thing happens. You all know that. Sometimes you might use see a cross-section times branching ratio on the y-axis, but essentially it's like the frequency, and this is the x-axis is the actual variable you are setting limits on. The first, let's look at the simplest one, that one called theory with n squared LO and next to leading log corrections. I know Stefano might talk about that. Ask him. But anyway, so what is that theory line? You take your theoretical model, because as I said, when you are doing a search, you need a theory model. Sure? You run your theory model through your experimental analysis, calculate the cross section for each mass point. So you essentially generate simulations for each mass point you want, and that gives you the red line. Then you actually look at your background simulation, right? Even before you look at data, you look at your background simulation. I mean, of course, you finalize your way, how you estimate your background. There are many different techniques. We'll probably go into some of those. You can also use machine learning. People have used that. I have some examples of that as well. But at the end of the day, you set your analysis to be most sensitive to the signal, but you essentially make a distribution of this mass and see how many events you get from the background. And that's your dashed line, the dashed black line. And then you take 1 sigma and 2 sigma variations. That's your Brazil bands, the 1 sigma up and down with respect to the dashed black line is, yeah, the one is green, 2 is yellow. So even before you looked at data, you have established how significant your analysis is, in the sense that what's your background contribution likely to be, and what's the uncertainty on the background estimation. After that, you open the box. You do the same thing with data, and then you get the solid black line. And then you have this plot. But how do you read this plot? The first thing is, if your observed The first thing is your observed and expected should be reasonably similar. Otherwise, you probably have not done your analysis right, because your observed is the data, expected is the background, right? Your background estimation, I mean, sure, if you don't see new physics, that's implied. After Higgs, we haven't. So if you don't see new physics, your background and data should roughly match up, which you can roughly see they are. I mean, at least they should be within 1 or 2 sigma. But the most interesting thing is this point where the red line is intersecting the expected and the observed line. The fact that you have observed less events in data compared to your theory prediction means that theory model cannot be valid till this point. I think that's the most important thing we want to talk about. So below whatever the cutting, like 1400 or whatever, 1450, there cannot be any new physics, or there cannot be, yeah, in this case there is no new physics because the expected and observed are matching and they are both way below the theory prediction. Does that make sense? So whenever you see a limit plot like this, you try to figure out where the intersection happens. Below that, it's excluded. So this model, whatever this model may be, is excluded till 1450, and then what happens after 1450? We can't say anything, because the model cross section is lower than what we observed. So we don't know if there is, I mean, of course here the data is actually slightly lower than the expectation, so probably there is no new physics. But in principle, if it's so low and it's a log scale again, it can get absorbed. So you can't make a definitive comment. Is that clear? Because again, as a theorist, if you can't read a limit plot, then that's a problem. Useful to anyone? Yeah, thankfully. So that's how we read a limit plot. I'll upload the slides so you can read about that later, but that's essentially what I explained. Also, as an experimentalist, why limits? Because we all want to find new physics, right? Even with your machine learning things you are developing, you want to help us to find new physics. But this is again a very biased experimentalist view. Out of the 100 new physics models we are looking at least 99 are wrong. Probably all of them are wrong. Once we do a proper analysis of that final state, we can probably exclude all of that. But, and as PhD students, I think this is super important for all of you to realize, null results are important. Even if you don't come up with a ground-shaking discovery, you still have learned something. And publishing null results is underrated, but I think we should do it, because you spend 2 years of your life working on a particular problem, and then somehow nothing great comes out. But you still learned a lot, that this doesn't work, that doesn't work. If you don't publish it somehow, someone else 2 years down the line is going to spend 2 years of their lives doing the same things and not getting a result. So even for experimentalists, I mean, we always publish null results because people can't graduate. I mean, no one is discovering new physics. After 2012, none of us have discovered new physics. And sure, people have done measurements, measured alpha s to an unprecedented accuracy, but at the end of the day, all the searches have null results. But people have published, gotten jobs, gotten awards, whatnot. So as younger, like young PhD students, I think this is something we don't emphasize enough, and I wanted to do that. Right. So what do? We reconstruct objects from detector information, and then we decide on sensitive observables. The example you saw, we were using something called HT, something called MT. We have to then estimate the background, and then either look for new physics or measure things at particle level. Again, some terminologies for people who have never seen these things. One collision is one event, that's how we say it. As again, you know, outcome of collisions is probabilistic. So we don't have an exhaustive list of possibilities. If we did, there would be no new physics hiding anywhere, right? So there is always hope that you have new physics processes with very little cross section. I mean, I think there was a discussion about if the new physics contribution is very high, you would have seen it. And then the cross section, as I said, is essentially a frequency of how often a process occurs. And then in experiments, you also hear some term called luminosity or integrated luminosity, which is kind of a number dependent on the machine and everything. And then we use something called integrated luminosity, which is, I mean, in all Atlas CMS papers, you see 139 inverse femtobarns. So that's the integrated luminosity. If you multiply that by a cross section for a particular process, you actually get the number. And the luminosity is essentially measured in 1 over area. The cross section is measured in area, historical reasons, fixed target experiments. You all know that. So one of the objects we have, and this is actually where the whole, I mean, this is not actually, okay, this is where the machine learning application starts. And when I said that, I realized I'm going to skip over the machine learning in trigger. How many of you know what a trigger is? Okay. So when you collide protons, we end up colliding 40 million, if I'm saying the number right, collisions per second. We have to transmit that data. I mean, the detector captures those all collisions. Then we have to transmit that to our storage element and save it. We cannot save those many events. It's just impossible in terms of electronics, in terms of bandwidth and everything. But that's not so bad, because nature is lazy. Most collisions that happen are extremely boring. Low momentum transfer, just a few tracks, nothing exciting going on. At least, unless you are a fan of diffraction or you believe in instantons and soft QCD things, those are not high energy objects you are expecting new physics in. So the fact that we throw away 99% of the events, I mean, I'm just paraphrasing here, it's not a terrible thing, because those are probably not the candidates of new physics events anyway. So for that, we need something called a trigger, which makes a quick decision on if this event needs to be saved or not. And it does that by reconstructing the objects at a very raw level. It's not a fine-grained reconstruction as we are. It's probably just going to look at like how much energy deposit in the calorimeter in that event, if that's a certain, over a certain threshold, keep. And we have different triggers corresponding to different objects. We have electron triggers, which tries to see if there is an electron with a certain energy in the detector. Then you keep the event. Then there are muons, photons, missing energy, HT, jets, of course, large radius jets, small radius jets. So we have different trigger streams, and everything gets their own little bandwidth so that we can save all the events. Now, one event can be saved in multiple triggers. That can happen. Event can have leptons and jets and missing energy. So trigger is super important. Now, Atlas hasn't, as far as I know, hasn't used machine learning in triggers. LHCb experiment, which is an experiment which is focusing on mostly B physics, they have used machine learning in triggers successfully for quite a few years. But I'm not an expert on that, so I'm not going to go into that, but just wanted to mention that. So what are the objects you see? Charged particles. And this is like a very schematic drawing. So the wiggly green lines are charged particles. Now, can anyone tell me why those lines are carved?
There's a magnetic field.
Absolutely. There are magnetic field in the detector which carves the charged particles, which is important, because that means we can then measure their curvature. From that, you can measure their charge, you can measure their momentum, first year electrodynamics, something like that. Electrons. So the first layer, the first layer is the tracker, which is mostly a gaseous thing where charged particle pass through We call them heats whenever they interact with like an atom of the medium, and then they emit light. Electrons are essentially measured at the next layer, which is called the electromagnetic calorimeter. They are optimized to stop electrons. But when you have electrons, they are also charged, so they would have a track. So the blue line and the orange energy deposit in the EM calorimeter. Photons, very similar to electrons, no tracks. Muons are heavier, so they pass through everything. And then the outermost layer is called muon chambers, where you detect the muons. Hadrons, which would use a lot to form the jets, are essentially sprays at the hadronic calorimeter, as you can see, and the missing energy, as you know, it's typically neutrinos in standard model, but you just have an imbalance of energy. Yeah, so you said you guys know what missing energy is. I'm going to skip over that. Jets. How many of you know how jets are reconstructed? Not too many. I know too many, you know. So, again, you are theorists, so I don't think I need to explain QCD to you. Essentially, asymptotic freedom, things that the attraction increases when the distance increases, and then you cannot have free quarks and gluons. You know that. I don't have to go to that. So, what happens is, or how we think it happens, is from a gluon, it splits into a QQ bar pair. The quarks emit more gluons, they split into more pairs, so on and so forth. And then at the end, you have these hadrons, which are colorless objects. Those are the ones we see in the detector. I mean, you have unstable hadrons, they decay into stable hadrons. But at the end of the day, we have hadrons. And hadrons decay in hadronic calorimeter. You collect them in these conical objects, which you call jets. That's like a classic what we call dijet topology, and this is we're in Germany, so let's call it Mercedes topology.
I think he has a question.
Yeah, sorry. Yes, please.
Maybe this is a stupid question.
No question is stupid question.
The baryons start forming at the beginning of the jet and the mesons more towards the end. I'm not sure if this is just an effect of the Doodle thing or if it's actually a physical thing. Baryons form earlier in the jet relative to mesons?
I think this is just like a schematic picture. I don't think that's. I mean, different hadrons have different lifetimes. So I mean, I don't know offhand if average lifetime of baryons is less than mesons. I don't see why that would be. I think this is just wherever I took the picture from. I think so. We can look it up. As far as I know, the word jet actually comes from jet d'eau, excuse my French, which is the big water jet in Geneva Lake, which many of you probably have seen. Apparently, that's how the word jet came. This is like a picture of a nice jet in our detector. Now, jet making. So, as I figured, there probably a quarter of people are familiar with jet forming, rest are not. So I'm going to explain that, because the way you do jet tagging does depend on how you make the jets. Now, unlike electrons, photons, muons, jets are not fundamental objects. The fundamental objects are hadrons. We make jets just for our own convenience, so that you can use a jet as a proxy for a quark or a gluon. There are few things you need to keep in mind when forming a jet, like what are the inputs we are going to use, how we are going to combine them, and what would be the size of the jet. These are three things which are important. Now, historically in Atlas, till say 2018 or so, we used calorimeter objects as jets. So you have, this is the center of the detector, this is your energy in the calorimeter, you have energy deposits, and then you take the energy deposits. It's slightly more complicated because the calorimeter actually is three-dimensional, like this, the clusters of energy we see in the calorimeter are what we used to call topological clusters. So they're 3D objects, so there's angle information and depth information. From that you can measure how much energy, so we use those things in jet making. CMS has always used particle flow objects. What that means is you combine the information of tracks and the calorimeter. Why do you do that? Because calorimeter, while it measures the energy very well, is is not as accurate measuring the direction. Where for tracks, the charged particle tracks, they are a very precise indicator of the direction. So you combine the information, you form what we call particle flow objects, and use them as jet inputs. Now, of course, for charged particles, it's easy. For neutral particles, you don't have tracks, so you still depend on the calorimeter objects. So that's what we use as inputs. As theorists, I'm sure I don't have to explain IRC safety to you guys. The whole idea is if you have two jets and then you have a soft glue-on radiation from one of the quarks, then our jet algorithm should not merge them. That's called infrared safety, and collinear safety is if you have a collinear emission, that should just be part of one jet, that should not change the whole structure of the jet. So that's something you have to keep in mind when you are writing a new jet algorithm. I have seen people writing machine learning based jet reconstruction. I'm sure they keep this in mind. I haven't looked at the details. Every dog should have a cat. Yeah. So there are two broad classes of jet algorithms. The first one we call is bottom up, where you operate in the momentum space, and I'll explain this in slightly more details. You combine two particles in momentum space and you form the jet. And the top down approach is you form a cone, you see what particles get inside it, then that's your jet. The second one is typically not IRC safe, also there are IRC safe cone algorithms. So the formula we use, we calculate for every object I and j, which every input object I and j in the whole event, we calculate all the dij's which are the minimum of their momenta raised to the power p or rho, let's say rho, momentum square, 2p, so sorry, squared rho, then delta y square plus delta phi square, which is their distance in angular space. We use this funny rapidity azimuthal angle coordinate. R is the radius, which you are going to set by hand. So for every two particles, we calculate that, and we also calculate something called dIb, which is the distance from the beam axis, which is that, where there are three choices for p or rho, corresponds to three different jet algorithms. 1, 0, minus 1. If it's 0, there is essentially no dependence on the energy, it's only on angles. 1 and minus 1, I'll explain the significance. And then the way the algorithm works is find the smallest, so let's say these are like different input objects, you try to find the smallest bit of dij's, let's say these are the ones, you combine them, you merge them, you add their momenta, you keep doing this till everything is merged, and then in this case you have two jets. Yes?
Could you come back a little bit?
Sure.
What you say about the sequence and the other type of algorithms. I couldn't, these three kinds, aren't they like the second type? You know what I mean? Like if you go back, one more. Yeah, sorry. One more.
Sure.
This. So you have the sequential recombination algorithm.
That's what we're doing.
Algorithm. I taught the KT, anti-KT, and Cambridge outing. I don't know how to say that.
That's fine.
They all or Kalm algorithms, but I'm not sure. So maybe I'm not.
No, okay. No. So we are forming cone-like objects. But the cone algorithm, the way historically, again, the names, we are physicists, we are not terribly good at naming. The way cone algorithms worked is you started with the highest energy or highest PT object, you made a cone of a certain fixed radius around it, then you see whatever falls in the cone, and then you move the cone around if the kind of the center of mass moves slightly. So that's cone algorithms. The one I'm doing is sequential combination, simply because I'm just combining two objects one at a time. I'm not starting with a cone and seeing what's all inside a cone.
Oh, I see. Okay.
No, good. Okay, so now that I've stopped here, so the exponent 1 and minus 1, so 0 essentially means this term goes away, right? There is nothing there. So the combination only happens based on the angle between the objects. When it's 1, the combination happens from the highest PT object to the lowest PT object. So the way the combination happens, in fact, the way I showed it here, you take the highest PT objects and then, I probably reversed it, yeah. So, yeah, no, so that's right. So that's how it happens. So the highest PT object and then you keep adding things. On the other hand, in anti-KT, you start with the slowest object and then you keep adding the highest PT objects, and that has implications. So I'll upload the slides. So I mean, I made a very simple example where I actually took 4 particles, calculated their Dij, so that you can actually hands-on see how we form jets. I'm not going to spend time on that, but this would be in the slides. What I want to show you is the finished product. So for KT, where you start with the hardest and then you build up the jet, typically what happens, because you are adding soft towards the end, you get very irregular shaped objects. Whereas when you use -1, you get roughly circular objects. And experimentalists love circular objects because we have to calibrate the jets. If we know the area of the jet more precisely, then it's easier for us to calculate. There is pile-up contribution, there's a lot of other things. So it's easy for us to calibrate and clean up the jet rather than those ghastly objects which you can't deal very well with. So that's jets.
And I wanted to be sure also about
Yes.
symmetry. As far as I could understand when I was studying this, the symmetry also is like easier to process during the treatment of the data, not just for identify like pile-up and etc., but also for if I want to use in a machine learning or something, it's easier to do transforms or something. Is that right?
That's probably true. That's probably true. One case we don't really like anti-KT is when you are doing jet substructure, which I'm going to come to next. When you want to kind of disentangle the whole jet formation and walk back, then if you are walking back from like the softer particles to harder particles, it's easier to see the whole history. Other way around, it's a mess. So there are pros and cons for both. But yeah, what you said makes sense. So in next or the last half an hour today, we are going to talk about searches and stuff David was mentioning. So the most common form of search is what we call bump hunting. What do you mean by that? You have something like a mass. It can be if you are looking for a dijet system, the dijet invariant mass. If you are looking for a heavy Z prime, you reconstruct the Z prime in a certain way, it's that mass. So it's some mass you are looking for. Standard model background almost always is a steeply falling function. If there is new physics, if there is a decay of a heavy particle X into whatever you are looking for, then you should have some excess events at some values which would show up as a bump in your standard model smooth spectra. Now, of course, this is an exaggeration. I mean, you don't see such a big bump. You would probably see something very, very tiny. I might have some more plots later, tomorrow, day after. But that's like the classical way of looking for new physics, which I think David was mentioning. But there are other ways of looking at new physics. Let's say you know your signal has a specific characteristic. Let's say, for example, let's say it has 4 B jets, a certain amount of missing energy, and 2 leptons. I mean, I'm just making this up. Then what you can do is you can apply some selection based on your signal. So always, what you always do, and I think I got a question there, what you always do is you have your signal simulation, which almost always for us means you have an UFO, which you guys are extremely familiar with. You run it in MadGraph, but that only gives you parton level events. Then you add a shower generator toward like Heroic 7 or PTI 8, which are the most standard ones, and then you get particle level you get particle level events, which are actually like things you get seen in the detector, and then you pass it through detector simulation. We'll talk about that tomorrow, how we use machine learning in FastSim and stuff. I think some others would as well. But anyway, so when you have your signal, you look at all the signal characteristics, multiplicity of objects, and PT distribution of objects, angles between different objects. Based on that, you come up with an optimal selection. And then you're not always bump hunting. You just want to see if you expect from your standard model, from your background prediction, which how we validate it, I'm going to come to that. But let's say you expect 50 events. And then you look at data and you find 51 events, you wouldn't be too excited. If you found 70 events, you probably would be. If you find 45 events, you would be like, probably I overestimated my background. So that's what we call a cut and count method. You just count, you apply some selections, you just count events in a specific selection and see if there is new physics. Missing energy, as you know, comes from neutrinos because they don't interact with the detector, pass through, so you have an imbalance of energy for momentum, and that's missing energy. Having said that, if we produce dark matter particles in our collision and they pass undetected, they would also give you missing energy. And a typical question we ask in our vivas to students is, how do you even distinguish what is from if you have missing energy? Is it from neutrinos or is it from dark matter? Now there is no obvious answer. But again, simulations comes to your rescue because for the standard model processes, you know which standard model process would produce neutrinos. And so far, we model most of the standard model processes reasonably well, let's say mostly within 5 to 10%. I'm being very conservative here. So we know how the missing energy spectrum would look like, what the missing energy direction would be. From neutrinos. If your missing energy spectrum is dramatically different from that, then you would get excited. Unfortunately, that hasn't happened, but that's how we can look for dark matter. The other thing we can look at, which is kind of like cut and count, is signal strength. You expect in a specific channel 500 Higgs bosons, and you see 700 Higgs bosons. Then you would get excited, something else must be producing those extra Higgs bosons. I mean, we typically define it in terms of a mu, which is signal strength. This is essentially like how many you expect and how many you get. So these are some of the ways we look for new physics. But the most important thing is the background. And all your anomaly detection fancy algorithms are, or most of them are designed to see like you can enhance the signal over the background. Now there are 3 types of backgrounds, which I think as someone who are trying to develop algorithms is super important for you to know. The first thing is irreducible, which is what you would expect. It has the same final state as the signal you are looking at. For example, Higgs to ZZ, a common golden channel for leptons, one of the discovery channels. But you can also have standard model ZZ production with a much higher rate than the Higgs because standard model. So that's a irreducible background, same final state. And that's probably intuitively obvious to everyone. But then there is a whole class of background which is pen in the wrong place. It's called reducible background, where a priori as a theorist you would not even think they are backgrounds, but they are. For example, I think there was a very quick discussion about Z2EE, like I think David mentioned. Now, I think someone asked, why can't you just figure out what is Z2EE? Sure you can. You take two electrons, opposite signs, reconstruct their mass, they're in the Z mass window, bingo. However, because jets also deposit energy in the electromagnetic calorimeter, and jet reconstruction happens completely independent of electron reconstruction, every electron is reconstructed as a jet. And okay, so let me take a step back. I mean, before pandemic, I mean, I always say this, particle physics was the original trendsetter in social distancing. Whenever you had an electron close to jet, we removed one of them because they are the same objects. I mean, mostly an electron would always form a jet, and we call this overlap removal. Many of you know this. Now, that's all good, but a lot of times a jet would be misreconstructed as an electron because it would have certain leakage in the energy in the M calorimeter, it would have charged hadrons, and we would actually think that's an electron, not a jet. Now, you might say, oh, that's not too much. I mean, if you ask me how many times that happens, I would probably say like 5%, 4%, something like that. So that's not too bad. But then you have to remember, the most ubiquitous process in colliders is jets. Jet cross sections are orders and orders and orders of magnitude higher than everything else. So even if a small fraction of jets are misidentified as electrons, you would have a lot of events where an electron is not an electron. And that's a classic example of reducible background. Of course, you can apply a tight electron reconstruction algorithm. There are things you can do to alleviate that, but never 100%. And this is true for a lot of things. I mean, jets, I have put it. So that's something as an experimentalist we have to deal with that. Calculating the background or estimating the background for irreducible process is easier because you know what you are dealing with. This you need to think, what are the things that can sneak up on you which you didn't expect, and that's always a challenge. And then, as I said, the combinatorial background is when you accidentally pick the wrong combination object, so don't reconstruct the right top or the right Z or the right Higgs, as the case may be. Now, the way a typical analysis works, so we apply selection cuts. What I mean by that, we apply PT and eta requirement on the objects, partly because the detector has certain extent. I mean, you cannot go more than 2.5 in eta, plus minus 2.5 in eta for tracks. There is no tracker beyond that. Also, we know like some part of the detector is less efficient and blah blah. So, and we know that if we reconstruct electron below 7 GeV, it's probably jets in most cases. It's messy, so you want to apply a certain PT cut so that you get good clean electrons. You try to get good clean electrons. So you apply that. And then you also look at, as I said, the signal characteristics, different distributions for signal and background, and that's what you do in machine learning. We'll come to that. But the most important point is, and I'll come back to it over and over again when we talk about this anomaly detection, unsupervised learning kind of things, that humans are biased. I mean, that's a trivial statement, but we are. Some of us are extremely optimistic about finding new physics. So the way you would set your cuts, maybe you try to see, you would like want to find new physics. Some of us are more cynical, like no new physics ever going to exist. So you would make that decision. Now, if you look at the data, before you decide on this step, your bias is going to play a role. So what we do is every search analysis is blinded. That means we decide on a signal region where we expect our signal, as David mentioned. We do not look at the data in that part before a lot of other steps, which I'm going to mention now, because we don't want to bias ourselves. So every search is blinded. I'm sure you heard the word. So we divide the events into signal region where you expect the signal to be, And then somehow you have to have confidence in your background estimation in your signal region, because even before opening the box, even before looking at the data, you need to have an accurate estimate of background in the signal region. Now, you haven't looked at the data, so how can you say it's accurate in the signal region? So that's why you have what we call control regions and validation regions, which are orthogonal to the signal region in terms of, let's say you have looked at, people have looked at this part of the mass spectrum before and haven't found new physics. So you want to make your background prediction here and check that it matches with data here. Here you are allowed to look at the data in the control region, and maybe then you take this part, which is where also there is no new physics, and make sure your estimate actually matches. We call that validation region, and then finally you look at the signal region. And then once you open the box, not much you can do. If you see a disagreement, I mean, ideally you shouldn't do anything. If you see a disagreement, the experiments get very upset and then they make you do things. But so I mean, just an example. So let's say you are doing a search where in two variables, so it's the mass of leading jet and the mass of subleading jet in a 2D event, and maybe this is where you expect the signal. So you are plotting essentially signal model, and the blue part is where you not expect a signal, and then you define your control region in the phase space where you don't expect a signal. Typically, validation regions can have some signal contamination because you can't restrict it completely. Of course, they have to be orthogonal to the definition of the region in the phase space, but they can have some contamination, but you hope it's not that much. And then you validate your background estimation in the validation regions. Sometimes you have multiple validation regions. Typically, if you have multiple standard model processes contributing to that search, let's say you have TT bar and Z plus jets and W plus jets, you might even have 3 validation regions, each focusing on each background, so that you can model, you have modeled each background correctly, you can validate that. Now, this is an extreme example, but it can happen that in the control region, the data and the simulation are not on top of each other. It happens more often than you think it happens. Now, why is that? And also, like a cautionary tale, if you, as a theory, is developing an algorithm based on the simulation, and the simulation doesn't describe the data, then is your model learning features of the simulation? That's the question you always ask, but let's go back to that. Is it modeling? Is it because we are modeling the background in leading order, we should have modeled in next to leading order or in square leading order? Sometimes that helps. Are we missing an electroweak correction? That sometimes helps. Sometimes it's a calibration issue that the calibration that we applied on simulated events is not performing, or somehow there's like some dead elements in the detector which you didn't consider, so you have to fix for that. But sometimes we just can't figure out. We are left with this. This is in our control region, and if I stay with that, I won't even be allowed to open my box. I won't be allowed to unblind my data, because I clearly can't model my background in the control region. And then whatever background estimation I get in the signal region, who is going to trust it, right? So then we use a sledgehammer, which is aesthetically very not pleasing. We do something called reweighting. We just take the ratio in each bin and fix the simulation so that it describes the data. And at that point you are like, why? But that's the best we can do. But then we look at validation regions with the same reweighting factors and see if now in the validation region you have data MC agreement. If you don't, then you have to go back to the drawing board again and do something. And only when in the validation region you have data MC agreement, then you open the box. So those are the things these are the battles we fight when we try to publish an analysis.
I didn't understand that. How did you get the reweighting factors for the signal region of the validation region?
so you get the reweighting factors from the control region, and this is, let's say this is a particular variable. You use the same variable in the validation region, you bin it in the same variable, and right. So of course this variable cannot be the variable you are using for blinding, for orthogonality. It has to be a different variable. So let's say this is PT, then I would, or your main variable is PT or mass, and this may be eta. So you have to, right. So you have to derive the reweighting in a defined variable so that we can apply it. Thanks for that. Yeah. Yeah. So different ways to estimate the background. Yeah. I'll just show some pictures. I think that's best. So this is like the classical sideband method, where you have like a falling background or roughly a steady background. You expect a peak, and then you decide on some sidebands. Just so this is your signal region, and you kind of figure out that if you extrapolate this, you would get the background. I mean, roughly, you essentially fit the line, and you check the goodness of fit with the background, and you expect that standard model would be predictable. One of the ways, well, we do this resonance search, especially at high tails, is we know the standard model background would be a steeply falling background, and we try to fit it with functions. Now these functions have been just tested over the years. We have a bunch of functions we use for this kind of backgrounds, and what we do is, we try to fit the function. So let's say this is our control region, validation region, signal region. So this is where we fit, and then we try to see if that explains the data in the validation region. A lot of times to derive uncertainties, what we do is we use different functions, we use different windows. So rather than using the full control region, maybe use this part, sometimes we use sliding windows. So this part, this part, this part, this part. You make many fits, and as you can see, in the tails they can deviate significantly, but that gives you a conservative estimate of your background in the signal region. And then you would open the box and see where these data points would lie. The other method we use, which is not very machine learning at all, is we take two variables, two uncorrelated variables, or mostly uncorrelated variables, and we divide our 2D phase space in A, B, C, D 4 regions based on where our signal region is, because they're orthogonal, and the others can be control region, validation region. And then simple unitary method, number of events in block A should be given by this unitary method, and then you calculate that. It only works for certain cases, but yeah. I have what? So yeah, I think I can do like 10 minutes of this. Yeah. Right. So now I'm not even going into proper machine learning, but so the whole idea is you want to discriminate something against something else. It can be electrons against jets, it can be signal against background, x and y. And this is again very, very basic. So let's say you have two variables, the red blocks are the signals, the blue triangles are the background, and you want to discriminate. I mean, this is what you get. Now, of course, historically we have used what we call rectangular cuts. So you say, oh, variable 1 should be smaller than this for this to be signal, variable 2 must be smaller than that for to be the signal. But as you can see in this completely made up example, that it doesn't work very well. I mean, it does its job. There is some contamination of background in the signal, there is some signals you are losing. But then you can try to be more creative. You can try to still use a straight line, but in a more creative way so that your purity of selection increases. Or you can try to be even more creative. Who is preventing you? You can define a cut like a nonlinear nonlinear cut or nonlinear decision boundary. Now, as human beings, as David was saying, in 2D I can do that. But if this is in n dimensions, where n is a large number, doesn't have to be very large, even if 5, humans cannot do this. And that's where whole your fitting thing comes in, right? So again, I'm not going to go over that. You guys are experts, I'm a user. But essentially the whole idea is you want to form an n-dimensional decision boundary, and then you try to map it onto a single discriminating variable, and then you cut on that variable. One of the things, again, you probably are aware of, but I wanted to highlight, because we are physicists, and I know, and we'll go into that, all of that, you can start with like the most basic low-level objects, like 4 momentum of everything. That's fine, that does its job. But I always feel like, as a physicist, I know certain variables are more useful for this particular topology, this particular signal. So we can form variables, use that, or transform the variables to bring about features using our physics intuition, rather than asking the machine to do everything. They do it very well, but yeah. For example, W boson transverse mass, sometimes you scale variables by the center of mass energy, which makes it easier. I'm not going to do that with you guys, you know all of that. But I found in Twitter, I didn't make it, but whenever, people get all in on machine learning, I'm like, we have to be careful, right? I'm just going to leave it here, not explain it. I don't think meme needs explaining. No? Yeah. Many of you might have seen this. Right. And of course, that's the classic example of underfitting and overfitting mostly. So the point is, when I use just like a rectangular decision boundary, that's, I think in technical terms, we call it underfitting. You're not using all the features that's possible. However, I can also make this. Now, this probably is best for this particular scenario, but take a slightly different scenario of the same process, it's not going to work, because this is essentially based on the features, like very specific features of this particular distribution. So that's something you are always careful of. Okay, I think I'll do one object. I'll do the tau first. No, I'll do the tau first. I'll come back to this tomorrow. Yeah. So one of the funny particles is tau leptons, which unlike electrons and muons are not stable in collider scale. So they decay into neutrino and either electrons, muons, or quarks and quarks essentially. And so you have hadronic taus and leptonic taus. Typically leptonic taus give the same signature in our detector as normal leptons. So I think there are some very brave attempts by some people, but mostly whenever we say tau analysis in hadron colliders, we always talk about hadronic taus. And you reconstruct the visible part. Now I have a quiz for you. Why the hadronic decay of tau only contain odd number of tracks? Anyone? Anyone? Yes, exactly. Yeah, because tau is a charged particle. So it has to have 1 or 3 tracks. And those are the aspects we use. So we reconstruct taus as 1-prong taus or 3-prong taus. Now, I'm not going to go into the technical details of this particular machine learning algorithm which Atlas uses, but essentially the idea is it uses tracks and energy deposits, and I don't even know what all of this means, to be honest, But if you're machine learning experts, you probably know, I have put the reference somewhere. I will. But the whole idea is there are lots of variables we use, PT of the jets, tracks, angles, hits in different layers of the detector, which is something you typically don't use as theorists, but those are things we have access to, and the cluster things, and then they call the high level inputs, which are more like combination of different things. You actually form variables. And then I just put like 3 different distributions of a true tau or a fake tau. Fake tau is typically from multi-jet events. And you can see, I mean, there is some shape difference, but not a lot. And then you throw all of them in a machine learning algorithm, like RNN, BDT. I know there's discussion about which one is the best. And you get this kind of ROC curves. Now, how many of you understand ROC curves? It's a statement that people understand ROC curves better than limit plots. So, good. How many of you don't understand ROC curves? Dude. Okay, so I don't have to explain ROC curves. That's good. So, typically, this is better, right? Like when you go diagonally up, this is better. And in experiments, we use what we call working points. As in, you want, maybe you are doing a search which is looking at a very rare process. Then you want as many taus as possible, even if some of them are more like background-like. On the other hand, if you are doing a very precision measurement, you want to get only taus, then you would work at a very high efficiency point for taus, but which would mean the statistics would be less. You would get less backgrounds, but you would get less taus. On the other hand, you can work here where you get more taus, but more backgrounds as well. And it looks like the RNN do better than BDTs, which would make Tillman very happy. At least for Atlas tau reconstruction, this is what we use now. This is the state of the art. I think I'll stop here. It's 12:20. So I think we're supposed to stop at 12:15, so I'll stop here. We didn't really talk about machine learning except that one little diagram, but hopefully you learned quite a bit, and we can build on that tomorrow and go into more examples of machine learning in jet tagging and in all the things we talked about. Questions? I know people don't want to ask questions because everyone is going to blame that person for delaying their lunch. But please, I mean, I'll be around. Yes, sure.
Going back to the very first part of the lecture, is there any experimental reason to prefer an ESC jet algorithm over an unsafe one?
Over which one? Over which one? Sorry.
Unsafe. ESC safety or safe?
Okay, yeah. Experimentally, no. But the point is, you want to measure certain things and compare it with theory predictions, right? I mean, a lot of jet measurements are compared with theory predictions. And if you ask theorists to calculate things in an IRC unsafe way, they are not happy. So you want.
Ask Matthias.
Or they can't. So you want your variables to be IRC safe. Now we actually do things which are very IRC unsafe, like we cut a number of tracks for quark gluon jet tagging, which is a pet peeve of a lot of people because that's like a completely IRC unsafe variable, but that works well for tagging quarks versus gluon jets.
It's the only thing that works.
Yeah.
So yeah, thank you, Deepak. Not enough questions. Again, not enough questions. It's like you have from behind. You look tired already. I understand some of you have jet lagged and like entitled to look tired. The rest of you, just like stop not by asking questions. It's good for everybody. You, the speakers, everybody. So from that, thank you very much. And then we'll have lunch and we could reconvene. What was it at 2? Claudius booked in when is it?
2.
Hmm? 2:30? I forget what I put myself on the program. 2:30, but anyhow, you can find it on Indigo.
Let me check.
And it's
2:30.
2:30. And it's Stefano. Yeah. Oh yeah, white one?
No, can you